Welcome to the lecture on reviewing the building blocks to SEM. In this class, we're going to go over some of the key pieces that are important to know before we get into structural equation modeling. So as a reminder from last week, one of the things we had talked about is that you first need to have a really solid understanding of the principles of correlation and regression, correct interpretation of those results, and also understanding how to do data screening and measure selection. We're not going to talk about data screening and measure selection in this lecture today. We covered that in pretty good detail in multivariate and also advanced statistics, so go back to your notes about that, about how to go about screening data, cleaning data, selecting good measures. And so today we're going to talk a lot about correlation and regression and correct interpretations of those primarily because much of what we're going to be doing in SEM is all about, and the way that we interpret our results in SEM are very similar to how we interpret correlation and regression. So we're going to go over those principles here in today's lecture. So first of all, before we get into that, I want to review some of the key pieces that might be important to understand before we move too far. First, type 1 and type 2 error. So type 1 error is falsely rejecting the null hypothesis, where type 2 error is failing to reject the null hypothesis. So in other words, type 1 error is a false positive, where type 2 error is a false negative. The example I had given back in multivariate is that this is similar to taking a pregnancy test and it's saying that you are pregnant when in fact you are not, where type 2 error would be telling you that you are not pregnant when in fact you are. When we're dealing with type 1 error, we typically have big data, so we're much more likely to get a false positive because of the nature of p-values and how much p-values are affected by large sample sizes where we can find spurious correlations and spurious significance. So because of that, we tend to use a lot more effect sizes rather than p-values to determine the significance and of our results when we're dealing with big data and when we're dealing with type 1 error. This is the same when we're doing with multivariate statistics because this tends to be a big data analysis. Effect sizes are going to be much more important than p-values are. Versus in type 2 error, we tend to have small data and consequently p-value tends to be more important because we're not having that same issue with false positives like we do with type 1 error when we're dealing with big data sets, large sample sizes. So statistical significance testing. So we're going to take a little bit more time to talk about p-value and what p is less than 0.05 really means. So when we have a significant p-value, what does that really mean? Journals today, we tend to skip over this and what p-value really means. So p, what that really means is the likelihood of an outcome over repeated events under constant conditions except for chance, so sample error. So in other words, p-value is all about repeated similar events. So p-value of a single independent study is pretty meaningless, but when we look at p-value across multiple studies under similar circumstances, that's when we see where p-value tends to actually have meaning. So in other words, p does not apply to a single discrete event, but rather it is based on expected relative frequency over a large number of trials in the long run. This is one of the reasons why we need studies to be repeated under constant or similar conditions over time, so once we do that, then p-value becomes much more meaningful because then we can see where the reality or where the truth really is in these studies. So if you remember from multivariate, I've given this example. So I'm thinking of a number 1 to 10. Make a guess. And what's the probability of me getting that number right? Most people would say 1 in 10 or 10%. Well, it's only 1 in 10 over repeated events, over constant conditions. Really, you only have a 50% chance you're either going to be right or wrong under one single event. But over repeated events, you would have a 10% chance or a 1 in 10 chance of getting it right. So the top two fallacies of P when we are interpreting P. The odds against chance fallacy is that P indicates the probability that a result happened by chance. So remember, P is estimated for a range of results, constant, repeated results over constant conditions, not for any one particular singular result. It would be wonderful if we had a statistical technique that could estimate the probability of a single discrete event, but we do not have that. P is all about repeated events under constant conditions. So that's the odds against chance fallacy. The other common fallacy is the local type 1 error. So this is where people kind of take p-value and almost do like an r-squared kind of thing to it, where they say like, I reject the null hypothesis at the 0.05 level, therefore the likelihood that this particular decision is wrong is less than 5%. Again, type 1 error is a false positive. So this is like the guessing game we had just played a moment earlier. Any decision to reject the null is either correct or incorrect. It is only with sufficient replication that we could determine whether or not that decision to reject the null hypothesis was correct. And the whole less than 5% is only true with sufficient replication. So when we're interpreting our p-values and we're considering them, we need to keep in mind what p actually represents and what it means. Next, I want to review the central limit theorem, because this is so central to everything that we do in quantitative statistics. So I'd also really recommend, now that you've been through advanced statistics and multivariate statistics, to reread that book, Naked Statistics, that you had probably had assigned back in advanced statistics. It's a great book, and when you reread it after you've had these classes, you'll pick up a lot more, and you'll especially gain a much better, more thorough, and deeper understanding of the central limit theorem. So the core principle of the central limit theorem is that a large, properly drawn sample will resemble the population from which it is drawn. So over time, as we do repeated experiments and take repeated samples, the samples will differ one from another, but the probability that any one sample will deviate massively is very low. Now, so what's important again is making sure that we have repetition. We have repeated events across time. Another principle of that is the sample means for any population will be distributed roughly as a normal distribution around the population mean. So as we take more and more samples from this larger population and we take those means will distribute in a normal curve. Again, one of the reasons that we need to make sure that we're doing repetition in our studies and doing and looking at this again and again, because any single sample from a population can be anywhere in that distribution. But if we take multiple samples and keep doing studies over time, that will distribute, evenly. So a few other things about the central limit theorem. When we understand the central limit theorem, this helps us understand how we can make inferences when we take a large, properly drawn sample from our population. We can make pretty powerful inferences from our data. So, we can make powerful inferences from a properly drawn sample from a known population. If we have detailed information about that properly drawn sample, so if we know the variance, the mean, the standard deviations of that sample, we can make strikingly accurate inferences about the population from which it is drawn. If we know that that sample is a good representation of the population, then we can take analyses from that sample and apply it to the larger population. This is where we get generalization from quantitative statistics. Third piece, if we have data describing a particular sample and data on a particular population, we can infer whether or not that sample is consistent with the sample from that population. So we can know whether our sample matches our population or not, which is critical, because if our sample is not representative of the population of our interest that we're looking at in a particular study, then we cannot generalize this to the larger population, and our inferences are not very meaningful. Fourth, if we know the underlying characteristics of two samples, we can infer whether or not both samples were likely drawn from the same population. We do a lot of this work, especially in our ANOVA analyses, where we're comparing two groups or two different samples. We can know whether they come from the same sample, and in fact, in ANOVA, what we're often doing is hypothesizing that one particular group does not represent or is not representative of that particular population. That we have done some intervention that has changed this sample differently. So, for example, they are no longer part of the population that needs to seek therapy. They are now in the population that doesn't need to seek therapy, or the depressed versus the non-depressed population, or whatever it is that we may be looking at. So next piece, variance and covariance. Pretty much everything that we do in statistics comes back to variance and covariance. And SEM in particular relies a lot on the covariance structure of our data. So these pieces are really important. Variance is a statistical way to capture how much individuals vary one from another across a sample. So if we take a particular observation or a particular score or item, when we look at the variance of that, we're looking at about how much each person varies one from another. The higher the variance, the more variability, the more that they differ one from another. Variance is calculated by taking the sum of the squared distances of each observation from the mean. So we calculate the mean, then we take each score and we look at the distance. So we're going to look at the absolute value. If it's 3 below, that's 3. If it's 3 above, it's 3. So we take all of those, we square them to get rid of the negative signs as we take those distances, and then we just divide them by n minus 1. So our total number of observations minus 1. That gives us the variance of that particular item or that particular measure in our sample. In order to get the standard deviation, then we just take the square root of the variance. So a lot of what we're doing is we're looking at means and standard deviations and variances and covariances in our data. So the variance, and in fact, in any kind of quantitative statistics, we really need good variance. So we need people to be different one from another in order to do any kinds of analyses. The covariance is a statistical way of indicating how much two variables covary together. So correlation and covariance are very related. Correlation is the standardized version, and covariance is the unstandardized. So covariance is still in the units of the actual variables. So covariance really reflects that variability of x and y, in addition to the strength of their association, so how much they move together or apart from each other. A covariance matrix between 3 variables describes relationships between more than 2 variables. So we can have covariance structures with multiple variables in here. So consequently, when we're looking at variance, variance is a univariate statistic. So it's looking at one item, where covariance generally is a bivariate statistic, where we're looking at 2 items just like we do with correlation. So overall, what we're going to be doing and looking at is we're going to be looking at a variety of univariate, bivariate, and multivariate relationships. Univariate analyses are all analyses about one item. So mean, median, mode, variance, standard deviations about one item. Covariance or correlation is all about 2 items, where we're looking at a bivariate relationship. And then what we're ultimately going to be doing at SEM is multivariate relationships. So we're going to be looking at the relationships between 3 or more variables in a variety of ways, including mediation and moderation and group comparisons and longitudinal analyses. So we're going to be looking at lots of variables when we do this. But the bivariate and the univariate statistics are still very important because those are used to inform our multivariate relationships and really tell us a lot about the variables that we're going to be using in our studies. So next, I want to make sure that we review a bit about missingness, especially because this was way at the beginning of the semester in multivariate statistics. So we're going to take some time to review missingness. So types of missingness. If you remember, we kind of categorized missingness into, or the different ways that we handle missingness into 2 categories. And these categories largely depend on the rationale or the assumption for why we have missingness. So the first kind is MCAR, missing completely at random. Missing completely at random means that the reason that there is no data here, why we have missingness on this variable, is because anything unrelated to any other variables in the data set. So it's really missing completely at random. There's no reason for why this is missing. This tends to be really super rare in MFT and family science research. That's because mainly when we're giving out, when we're doing survey data, people skip items, and the reason they skip items are related to other variables either in our data set or variables we have not included in our data set. Where we tend to have missing completely at random tends to be in studies where we have data or surveys that are too long to give to a particular set of participants, so we randomize which items are given to participants. So it is completely random. Even in studies where there may be missingness because these questions weren't asked this particular set of participants, tends to also have reasons because those are typically not asked for a particular reason. You aren't asked this question because you aren't still with your partner. You aren't asked this question because you didn't answer at least a 3, on this other item we did above. For all of those items, what we're dealing with is MAR, missing at random. So the missingness on this variable is related. It's unrelated to values of variable unrelated to values of variable on X, but is related to values on one or more other variables. So in other words, there is a reason for this missingness, and it tends to be related to other variables or other factors either in our study or that we haven't studied. So it's not completely random, but it can be explained by other variables. This tends to be much more common. And when we are looking at the different ways that missingness is handled, all of them tend to assume either MCAR or MAR. And if you remember from multivariate statistics, everything that SPSS has in the version that you had is MCAR, assumes MCAR. So there were 2 methods that we had talked about, and then a third that you should never ever do. The first one is listwise deletion. This is the one that you most commonly used, especially when you're doing multivariate statistics, and was often the one that was just automatically selected for you when you're doing multivariate analyses in SPSS. So listwise assumes MCAR. So and again, if your missingness is at random, so MAR, you're going to have much more biased estimates. So there's going to be more error in your results. So what this does is it deletes whole cases with missingness on any analyzed variable. So across the 4 variables you're using in this multiple regression, if any one of those 4 is missing, that person is gone out of your study. So because of this, we can end up losing a lot of data, as much as half of your data, depending on the level of missingness on different items. That also means you are missing out on people that aren't answering certain items for particular reasons. It's changing your sample. So sometimes what you're going to be doing is reporting on your sample, and then your analysis is from a completely different sample because it's deleted out 20 to 50% of your participants in that study. So it can work well if you have large samples and if your missingness is missing completely at random, or MCAR. Because of this, it really increases your type 2 error because it's going to really reduce your sample size and really decrease your power in the study because, again, it's reducing your sample size. Pairwise deletion was the other one. This is one you can really only do if you're doing bivariate analyses because pair 2, it can only be done when we're doing 2. We looked at this in correlation analyses where I had you do both a pairwise and then a listwise deletion so you could see the difference between those 2. And essentially in pairwise deletion, what you're going to be doing is creating lots of different subsamples because every bivariate analysis is going to have a different sample, a slightly different sample, depending on who it brings in with that, because it's only going to take people that have answered both of those items on each pair, each bivariate analysis. Again, pairwise deletion, just like listwise, assumes MCAR. And so all participants who answered a pair of variables are used to estimate the covariance or the bivariate analysis between those variables, which gives you a lot of different ends. We don't tend to use this a lot because it's not very helpful most oftentimes to have a set of analyses where they're all different sample sizes. And in addition, degrees of freedom are difficult to calculate because we have different samples across different analyses. So this creates all sorts of issues when you're trying to do that. So listwise and pairwise both have pretty significant issues in handling missingness when we're doing analyses. Now, up until now, you've been stuck with SPSS, and unless you had the really expensive add-on for missingness, you've been stuck with either pairwise or listwise, and most often stuck with listwise because you're doing multivariate analyses. The third kind is mean substitution, the one which we shall not talk about, but this one likewise assumes MCAR, and what it just does is take the mean and plug that in anywhere there's missing. And if you remember, we talked about the reason this is really problematic is because people that tend to be missing when it's MAR tend to less often be closer to the mean. So because of that, we're reducing the variance of our population and we're pulling everybody in towards the mean, and it's going to create some pretty strongly biased and problematic errors in our data. So it both underestimates and overestimates depending on the level of missingness and the reason for it. So, like I had said in multivariate, please, for everything that is holy, please never, ever, ever, ever use mean substitution. It's terrible and awful, and we should never do it. All right, so now I'm going to talk about the two contemporary or more advanced ways of handling missingness and ways that you can handle it in SEM when you're using M+. Multiple imputation is the much more difficult one to do because it takes a lot of steps and work, but what multiple imputation essentially does is it produces a different solution for each imputation. So each missing value, it's going to find a value for that based on the steps that you do. So the first step is imputation. So it's going to fill in or impute all missing entries of the incomplete data sets. Not once, but 5 to 10 times. And then the software will automatically do this. And then it's going to analyze all those newly created data sets, integrate all of those into a final results, and find the best estimates for each missing value based on the data that it does have. So a combined parameter estimate is simply the mean of all the multiple imputation estimates for that parameter. So it's going to take it all over the place and create a mean around this. This isn't mean imputation, so it's not what we were doing before, but it's essentially finding the best estimate based on the available data and then imputing that and doing that dozens of times and then finding the best answer for that. So a multiple imputation does take a lot of steps because you're going to be doing this 5 to 10 times, but when you're done with it, you have a full data set with absolutely no missing values. So if you're doing some kind of analyses where missing values are really problematic, or this analysis can't be done if there's missingness in there, this is a really good tool to do that. So people that tend to use AMOS, which is the SEM software for SPSS, tend to do a lot of multiple imputation because there's a lot of things you cannot do in AMOS if you have missing values. However, we're not going to touch this one this semester because we're going to be using M+, which can simply do full information maximum likelihood, and full information maximum likelihood and multiple imputation have found to be largely equal in their biases, and their biases tend to be much, much less than the other two. The other three that we did that assume MCAR. Multiple imputation and full information maximum likelihood both assume MAR. So full information maximum likelihood, or FIML, it doesn't impute the missing values, but rather what it does is it takes all the available information to directly estimate parameter estimates and standard errors through an iterative procedure using log likelihoods. So if that doesn't make a lot of sense, that's okay. Computer does when you use FIML to find the least biased estimates for those when it's doing the analyses. So when it creates samples from this to do this, it'll do this like 500 or 1,000 times in an instant. And because this doesn't require all those multiple steps that multiple imputation does, and because it's been found to be equal in how much or how little it biases data, FIML has really become one that most people use because all you have to do is say in M+, I want to use FIML, and then you go. You don't have to do all those steps that you have to do in multiple imputation. So that's the one we're going to be using across this semester. Keep in mind, FIML does require normal data. If you have non-normal data, there is a more robust FIML that you can use in your analyses. We're not going to talk about that this semester because that would require a whole lecture on how to use the robust version of FIML. But if you have non-normal data and if this is a problem for you, please come talk to me and we can talk about how to use that more robust version and what the syntax is for that and how you use that when you're doing analyses. So there is an option, a more robust version of FIML that can handle non-normal data, but there's a lot that goes into that. So this semester we're going to be using FIML as we work through M+ and making sure that we have normal data. All right, now it's time to get to correlation. So now we've covered a lot of the foundational pieces around how we handle missingness and variance and covariance, as well as the central limit theorem. So correlation, remember that's our bread and butter. A lot of what we're doing in statistics is based off of correlation. When we're working with, except when we're doing ANOVA, we're really dealing a lot with correlations, and everything in SEM goes back to correlational research. So the understanding correlations is really important as we move forward into SEM, because at its core we are doing correlational research. We're just doing it much more sophisticated with multivariate analyses. So correlations are the building blocks of everything that we do, or most everything that we do at least. They are crucial to methods like regression and multi-level modeling, and they are crucial to a lot of multivariate analyses. As a reminder, correlation does not equal causation. So you'll see a lot of people when they talk, and I'll even do this when we talk about our models, we'll talk about predictive relationships. That's mainly because we have to do ordering when we are creating our models. However, unless you have met all the requirements of causation, which means experimental, longitudinal research, and a few other pieces, it's not causation. Even when we have longitudinal research, it's not directly causation unless we have a few other pieces. So correlation is not cause and effect, it's not causation. All right, so correlation is, when we're looking at the correlation coefficient, which is R, it goes between -1 and 1. And correlation tells us the strength and the direction of a linear relationship between two variables. So correlation, any kind of correlation analysis is just a bivariate analysis between two variables, and it's telling us about how well they move or don't move together. -1, a negative relationship is, remember we talked about two people passing each other on the street. So one's going up while the other's going down, and the more strongly correlated they are, the more strongly that passing relationship is. Where it's positive, that means they move together. And the more strongly correlated it is, the more they walk in sync together and walk at the same pace together. So when we're doing a correlation analysis, we're looking at each of the observations between the two variables and then looking at that cloud of those and essentially drawing a circle around it to identify the strength. The tighter that circle, the tighter the strength. And then when we look at the direction of it, so how flat or how vertical it is, tells us more about the strength of that relationship. A line that goes up like this will be positive, and then a line that moves from the left, starting at the top end, moving down as we move right, would be a negative relationship. So R, correlations, is simply calculated by looking at the degree to which X and Y, so each observation, covary together, over how much they vary independently. So R is essentially a ratio to how much they move together versus how much they move independently. And so if you remember when we talked about this, the larger the top end is compared to the bottom, the closer we're going to get to 1, versus the smaller the top end to the larger the bottom end, the closer we're going to get to 0. So if this is 10 over 1, that's going to be a much bigger number versus 1 over 10, which is going to be a tenth, a much smaller number. So that's why as they move more independently from each other, so the less they vary together, the closer we're going to get to 0. Versus the more they covary together, as opposed to how much they vary independently, the closer we're going to get to either 1 or -1. So correlations measure the relationship between two variables, or how much they covary together. So remember, covariance is the unstandardized, and correlation, Pearson's R, is the standardized version of that. So it measures the positive and the negative and the strength of that relationship, where -1 and +1 are a very strong relationship, and 0 is absolutely no relationship to each other. Generally, when we're looking at R, because it's a standardized statistic, it also works well as an effect size. Anything under 0.1, so between 0 and either positive or -0.1 tends to be really small. 0.3 tends to be pretty good size. 0.5 tends to be large. And then if you remember, anything above 0.8, we kind of assume that these two are actually the same variables, and then we have issues with multicollinearity when we're doing regression analyses. So above 0.8 tends to be really problematic, because then we're essentially saying we're measuring the same thing, we're just calling it, instead of saying happiness, we're calling it joy. So outliers in correlation analyses cause large problems for us because of how much outliers affect the mean and the variance that is used to calculate our regression or correlation coefficient. So let's take a look at this. For example, if we have this spread of scores, we can kind of see where the general direction is and also the strength pretty tight. So it's a strong positive relationship. But if in this data set we had these little bit of outliers out here, what would that do to our correlation coefficient? Well, it would make it much less strong, so much weaker. It would be much closer to 0. And it would also be much weaker because of how much those outliers affect our scores. So whenever we're doing any kind of analyses, when we talk about data cleaning, one of the most important things in data cleaning to do is attend to outliers, because outliers can really impact our results. Whenever we're doing any kind of research that uses correlational analyses, and because regression is based in correlation and SEM is based in regression, we need to make sure we attend to outliers because they will really affect our results. So in summary, correlations simply measure whether there is a relationship and variance between two variables. It does not measure causation, it does not measure cause and effect, and it's very important when we're writing up our results to use the language of correlation. So we use terms like link and association and related, and we don't use language like effect, caused by, impacts. We want to use our correlational research. 2, correlation measurements are only as accurate as our sample population. So if our sample is not representative of our population, we cannot make inferences on that population. We can't generalize. Outliers dramatically affect correlation measures. So because of that, we need to attend to potential outliers that could really impact our analyses. One last thing I want to cover before we can move on to regression is R-squared. So we talked about R-squared is typically used in regression analyses. It's one of our measures of fitness or goodness of fit that we use. So R in and of itself, while it is a ratio, it is not a proportion. So we can't say that because R is 0.05 that variable X predicts 50% of Y, or that X accounts for 50% of the variance of Y. That's not R. But if you square the R, if you just take R and square it, then we can talk about more proportion. So in this case, if that 0.5, if we squared it, we'd get 0.25, and then we'd be able to say 25% of the variance in variable Y is related to changes in variable X. So if you remember from regression, we use R-squared a lot to talk about the goodness of fit of our data, and also to talk about how much of the outcome is accounted for in our predictor variables. So R-squared is something that becomes really important in regression analyses, and we'll use it also in SEM. We'll have R-squared there, and we'll still use it to talk about how much our model accounts for our outcome variables. And that again comes from R. So if we're not attending to our outliers, if we're not attending to good data and have good psychometrics and have good representative samples, then our study is not going to be very useful because it's all based on correlation. All right, so next we're going to move to regression. So remember, R goes up and becomes big B. So we're going to talk about now, review some of the important pieces of regression that are important when we're doing SEM. If you remember, most of what we do in SEM is going to be regression results were interpreted the same way as regression. So let's first talk about the equation of a regression line. If you remember back in multivariate, we talked about the equation of a line. So if we take our x and y graph coordinates and we plot on an x and y variable in a few different places, and if we draw a line through those, the equation for that line is y equals mx plus b, where y is the y coordinate, x is the x coordinate, and then b is the y-intercept, so where the line intercepts the y-axis. And then m is the slope, and slope is rise over run. So the slope is how steep or flat is this line, this green line, how steep or flat is it? So when we're doing this is how much does y go up or down when x moves by 1? In regression analyses, that's what we're doing. When we interpret our results, we're saying when x goes over by 1, so when our independent variable increases by 1, how much does our dependent variable go up or down? That's ultimately what we're doing, and that's where we get into where we talk about and again, correlation analyses, we won't write it in this way, but when we're trying to predict where y would be based on values of x or based on values of a few independent variables, this is where we get how we're getting into predicting our dependent variable. So remember, in correlation, we're just kind of drawing a circle around this to essentially find how strong is this cloud. Is it super wide and weak, or is it really tight and strong? And what direction is it? Where in regression, what we're doing is we're going to regress a line onto those spread of scores and make that line where it has the least deviation or least average deviation from each observation. So we want those blue arrows overall to be as small as possible when we regress that line. So some of the fundamentals about this when we are doing regression analyses. Two things here. First, what we're actually going to do is propose a model. So we're going to take a set of variables and propose that they are related to some outcome, or they explain the variance of that outcome. And when we get into SEM, we're doing much more sophisticated modeling rather than just saying a few variables predict it. We're actually going to develop a model and say these are how these variables are related, and this is the way that these variables are related to each other. And then what we're going to do in simple regression is regress a line onto those. In SEM, the same similar concepts apply, even though it's a little bit more complicated because it's doing a lot of regression lines at the same time. So what we want to know is how well does that line fit the data? So how well does it explain the variance? How well does our proposed model fit the variance or fit the data? In SEM, that's essentially what we're going to do, except we're going to have a whole variety where in multiple regression we have basically two fit indices we're looking at. In SEM, we're going to be looking at about a dozen or half a dozen of different fit indices that all give us different information. But essentially what we're doing is looking at how well does our proposed model fit the data. The second thing that we're going to ask ourselves in regression is what is the slope of that line? Because ultimately what we're wondering about is when our x variable changes by 1, goes up by 1, how much does our outcome variable go up or down? So how much does that change? The rise over run. So when we run once, how much do we rise or how much do we fall? So the slope is our regression coefficient. That is our outcome variable. Occasionally, and this, we want to know the y-intercept, so the starting place. The starting place, the y-intercept, is really important when we get into mixture modeling or growth modeling, when we really get into some of that longitudinal data, when we're interested in not only in how people change across time, but we're also interested in where they start. So, for example, if you're doing like transition to parenting research, you're really interested in not only what that looks like as like marital happiness, what that looks like as parents transition into parenthood, but also how that might look differently depending on where parents are, where their level of happiness is at that start of that transition. And when you're doing growth mixture modeling, you can actually find different groups based on where they start and also how they progress across time. So we're going to review the formula for regression line one more time to make sure that kind of helps to kind of sit in your head a little bit more clearly. So again, the formula for line, y equals mx plus b, where y and x are the values of the y and the x coordinate. M is the slope, that rise over run, that's again our regression coefficient, and b is the y-intercept. So how we tend to write this is y equals b naught plus b sub 1 x sub 1, where b naught is our b and b sub 1 is m. That's our regression coefficient. So y sub I is the value of y for case I. B sub 1 is the slope. That is our regression coefficient, or m in the y equals mx plus b. B sub naught is the intercept. That's that b value in y equals mx plus b. And x sub I is the value of the predictor variable for whatever case, whatever participant it is that we're looking at. So, and if you remember too, we talked about error. So remember, when we talk about, and this is hopefully comes a little bit more clearly to you today, when we talk about error in SPSS, when we're talking about regression, we're just talking about the error of each value from that regression line. We aren't talking about error in the same way we're talking about error in SEM. When we talk about error in SEM, we're talking about the error of each construct, which in regression SPSS, it's assumed it's measured without error. There's no measurement error. In SEM, we can actually measure measurement error. We actually get a value for that. So when we talk about error here in the regression formula, we're not talking about measurement error, we're talking about error from the regression line. So remember, our line has error because not all data points fits the line exactly. We often call this residual. So again, it's understandable that you can get a bit confused here once we move to how we talk about residuals and error in SEM, because in SEM we're talking about measurement error of each item or each factor, where in regression here, what we're talking about is the error of each value from the regression line. So we're looking at that residual or that error here. So when you're looking at the output in SEM, or sorry, the output in SPSS, when we see that error term, it's associated with the beta value. It's the average error of each value from here. We're not looking at the measurement error, or the error of actually the error of variable x, or the error of variable z, or the error of variable y. So when we do that, what we're going to do is we're going to add the error term into our regression formula. So y equals mx plus b plus e. That's essentially what we're going to be doing. So once we get into multiple regression, all we're doing is adding in more independent variables. So y equals, mx plus b, but we're going to have different variables for that. So what that ends up looking like is we may have like marital qualities, our outcome variable, and then we're measuring warmth and hostility, and so we'll have an mx for both warmth and for hostility, as well as our error in our regression line and our y-intercept for those. So as a reminder, we did this in a little way in multiple regression where we're assessing model fit. So we're looking at how well the model fits the data. This principle becomes critical when we're doing structural equation modeling, because the main factor of whether you determine whether this model is acceptable or not is not about the p-values or the significance levels of our individual parameters or regression coefficients. What we're going to do is look at the model fit. If your model does not fit the data adequately, you reject the model, and it just doesn't work. And that can be really important to say, like, this theory proposes that this is how this model will look. We tested it and it doesn't fit. So the theory is wrong. Or at least for the sample, the theory does not seem to fit accurately. And I have specified it correctly and followed all the steps correctly. And my sampling was good, my measures were good, and it just seems that the theory doesn't fit. However, this alternative model does fit the data, and so we should be able to adapt our theory in this way, because this is how the model tends to fit, or what seems to be reality here. So in regression, what we're doing is we're looking at variance explained and the ANOVA table when we're looking at regression in SPSS. The variance explained is that R squared. So it's our correlation squared, where we look at, our variable X accounts for X% of variance in variable Y. The ANOVA table, is the F statistic in our regression coefficient. And in this, a good model should have a significant big F statistic, so bigger than 1. So in other words, what your F ratio is looking at the ratio of good data to bad data. And if your ratio is large, that means you have better good data than bad data. If it's small, closer to 0, then you have a lot of bad data compared to the good data. And then you're going to have a non-significant F statistic in your ANOVA table. And then you essentially say that your model doesn't fit the data. And in that case, you usually won't ever have any significant results when you're doing a multiple regression or bivariate regression in SPSS. And again, in SPSS, we're looking at the beta value. This will be the same thing that we do in SEM. We're going to be looking at beta values, both standardized and unstandardized. And we're also going to be looking at the R squared when we're reporting our results. The R squared and the beta value don't matter as much for determining how well the model fits the data, because we're not going to be using R squared as a model fit indice in SEM, but we'll still use it to help explain our data and report our analyses. So assumptions of regression. So we have all the assumptions of parametric statistics, because regression is a parametric statistic and SEM is the same. And we also assume that there's non-zero variance. We need variability in order to do analyses. If everybody is the same or really close to the same on a specific item, it's not going to be very useful to us in a regression analysis. Linearity. So this is a big one. Regression assumes linear relationships. If there is a curvilinear relationship, there are other analyses that need to be done. In SEM, we're going to assume the same thing, that there are linear relationships. If there are curvilinear relationships, that'd be a different kind of analysis that we're not going to be covering in this class. No multicollinearity, same thing in SEM. So in other words, we shouldn't have any variables that have an association of 0.8 or higher with their correlation analysis, because otherwise they're basically the same variable. So no multicollinearity, independent of residuals. So this means that the errors are normally and independently distributed. Now in SEM, we can actually deal with violations of this, but not only just of the error in the regression, but actually in SEM, we're looking at the actual residuals, so the errors and the measurement error of each actual item, each variable. And if there are associations between those, so if they are non-independent, if they're dependent on one another, we can actually correlate those and account for those relationships in SEM. So we can deal with this, this violation here very easily in SEM. And if you look at some of the examples I give or I gave last week, you'll see some correlations between the error terms in those models, which indicates that I accounted for those non-independent or those correlated errors for variables. Homoskedasticity of relationships means that variance of residuals do not vary across values of y. So in other words, that there is a heteroskedastic relationship, so in other words, they move together. There's not, there's a homoskedastic relationship. If there's a heteroskedastic relationship, then we have problems. If you remember back in multivariate statistics, this is an example I gave where there was like a cone-shaped relationship versus one that was tight together. So the example, I think it was either in the Fields book or Naked Statistics, I don't remember which one, is when we look at people going to a rock concerts across each day, and you look at a group of young people and how quickly they get their hearing back versus people who are in their 40s or 50s, and you'll see that the people in their 40s or 50s, as they attend more concerts, it takes longer and longer and longer to get their hearing back, so you get this cone shape rather than this even distribution. So that's the homoskedasticity of relationships. So interpreting regressions. So I've already said this a few times today, and I want to make sure that this gets just ingrained in your head, that when we interpret regression, and this is going to be the same thing in SEM, when IV goes up by 1, DV changes by beta. So if we're doing unstandardized, then that's in the actual units of the variables. So as the IV goes up by 1 unit, the dV changes by whatever beta is units. We're in standardized betas, and most of what we're going to be doing is with standardized. In multiple sample SEM, we don't use standardized, we only use unstandardized. But and most everything else, we're going to be using standardized results when we write up our results in the results section. Our tables will still have the unstandardized and standardized if you have tables. And typically, if you're going to do display a figure, you'll use standardized betas. So standardized is as IV goes up by 1 standard deviation, dV changes by beta standard deviations. And what I'd like you to do now is pause the PowerPoint presentation at this time and correctly interpret warmth and hostility for the dependent variable marital quality. So do an unstandardized interpretation and do a standardized interpretation of beta for this table. The next slide, I'm going to show you what the correct interpretations are, and I want you to try and do these yourself. So go ahead and pause the PowerPoint at this time and write this out or say it out loud and see how well you do when we get to the next slide. All right, so let's see how well you did. So if we're going to look at marital warmth or relationship warmth for this table, the standardized slope for warmth is 0.879, suggesting that for 1 standard deviation unit increase in wives' warmth score, so for this we're looking at wives reported marital quality is expected to increase 0.879. We typically round this to the nearest 2 decimals, so we'd say 0.88 standard deviation units after controlling for wives' hostility scores. So again, as warmth goes up by 0.88 as warmth goes up by 1 standard deviation, marital quality increases by 0.88 standard deviations after controlling for hostility. And then if we look at the other one, hostility, as hostility goes up by 1 standard deviation, marital quality decreases by 0.37 standard deviations after controlling for warmth. If we're going to go to the unstandardized, we would say as warmth goes up by 1 point, marital quality increases by 0.68 or 0.69 points, if we're going to round to 2 decimals, 0.69 points after controlling for hostility. Where for hostility, we would say as hostility goes up by 1 point, marital quality decreases by 0.61 points after controlling for warmth. And we can see, if we look at the significance level, the p-value, that both of these items are significant. In summary, regression is a statistical technique that allows us to predict someone's score based on the basis of their scores on several other variables. Now, it's ultimately a correlational analysis, so although we often talk about it in that way of predicting, we don't write about it in that way. We would rather say when we write about it that it allows us to look at the association of someone's score, the outcome variable, based on several independent variables. Regression is a way of predicting an outcome variable from one or multiple predictor variables, depending on whether they're doing simple bivariate regression or multiple regression. And multiple regression is also known as OLS regression, or ordinary least squares regression is typically what we're doing when we talk about it. The regression coefficients are used to indicate the expected increase in an outcome variable. So again, what we're doing, increase or decrease, I guess we should say. And beta is going to tell us how much that goes. So as our independent variable moves over by 1, how much does our outcome variable go up or down? So we're looking at that rise over run. So as we run 1, how much do we rise or fall? So next week, we're going to talk about model specification. So next week, we're going to start to talk about the rules about how you actually create a model and what is necessary in doing that. So that's coming next week. For the rest of this week, make sure you do the readings as you move next, and that you review your old PowerPoints from multivariate statistics and watch some of those old videos.